Hello, my name is Daniel Salkeld, and this is my presentation for Lab 2 Lines of Charge. Introduction. Our purpose is to produce a computational model and calculate the charge required to float one tape above another while considering the charge to be evenly distributed. Key principles. We need Coulomb's law, Newton's second law, electric field, E-force, and superposition. Why? Because this time we have distributed charges and we need to add their E-fields together to get the total E-field and then get the E-force. Um, Assumptions. The charge on the tapes was the same and evenly distributed. We need to assume there's no air resistance and that the charges are evenly distributed again along the tape instead of a single one. Main result, our charge was 3.063 times 10 to the negative 8 coulombs, and our magnitude of our E-force was 1.70297 times 10 to the negative 3 newtons. Here, to the right, you can see we use the E-rod formula instead of the regular point charge E-field formula to solve backwards from the force of gravity to the charge. Lab 1 data versus Lab 1 results. So you can see Lab 1 data is the same length as the tape as last time, same width. So you can see all the values here. Tape weighs around 0.2 grams, same distance, 0.04 meters. And then the old charge is 1.87 times 10 to the negative 8 coulombs for the positive tapes, and the force of gravity 0.00196 newtons. And we need this for this lab to solve backwards and find the charge, except this time again we're using the E-rod formula, and you can see all that in the orange and how we used that to mathematically calculate the charge in coulombs. And then to the right you can see our calculations from lab 1 to see how we found those last time. Experiment. Our initial conditions were just two uncharged pieces of clear tape. Our system was tape A and our surroundings were tape B and everything else. And essentially we rapidly ripped and unripped two tapes together to charge them, um, in simple terms at least, and then we observed their observations and interactions with neutral objects and other objects. And then we suspended one above the other and calculated the distance in between and the force of gravity. And we will use that in this experiment to solve backwards to determine the distributed line charge. Computational model. In the top left, you can see our constants and the same as last time, except the charge is different. And in line 34, you can see we defined the E-field function with all the formulas within it necessary to calculate the E-field. And in line 49, you see we defined, or at least the code was already defined, but we defined the line charge function, and this actually created the uniform distributed charges in the computational model, and we need this to calculate um, the the force of gravity and the E-force more accurately and within this context. And in the middle picture, you can see at the top, we created the distributed charges. We made 50 of them, and essentially the red is the top tapes charges and the blue is the bottom tapes charges. And then in the middle, you can see we scaled the E-force and the E-field. And then at the bottom of the middle picture, you can see we calculated the E-field at the top due to the bottom tape, and we calculated the E-force at the top due to the bottom tape as well by multiplying the top charge by the E-field at the top, which is essentially the same thing as F equals E times Q. And then in the bottom screenshot, you can see we created the Y arrow to represent the E-force, and then the yellow arrow to represent the force of gravity. And then the top right, you can see our picture and has the values we discussed before, the new E-force, the new or the same G-force, and the charge over single tape. And essentially, you may think E-force and G-force are different, but they're basically the same. I mean, it could be due to human error, but in this case, the magnitude is the same because they're both multiplied by 10 to the negative 3, but they're just slightly off. So it's still in near equilibrium. What if so if what if we have modeled the tapes as a single point charge in the previous lab instead of distributed like this lab? So essentially our results would have just been different. Our line charge again was 3.063 times 10 to the negative 8 coulombs, and our point charge was 1.87 times 10 to the negative 8 coulombs. So our results essentially would just be different, and the line charge would be smaller and more accurate. Um, and essentially, why do these estimates differ? They differ because we're treating the system differently. We're treating it more accurately. In real life, a tape will not have a single charge. It will be distributed because it's a long object. Now, it may not be distributed evenly, but it will be distributed. So potential sources of error: not measuring the tape correctly, not measuring the distance correctly, not handling the tape correctly, and just the assumptions we have to make. We have to assume it's evenly distributed, but it could really be not, and it could not have the same magnitude. Um, and again, like I said, the results would be different and our line charge would be more accurate, maybe slightly bigger or slightly smaller,